Hello, my name is Ramtin, and I'm going to present our experience on applying specification-based testing to a large industrial application. This is a joint work with my students and colleagues in University of Tehran. As I'm presenting at a formal methods conference, I feel obligated to start with this slide, but actually financial market has its own stories too. Maybe the most famous one is the case of Knight Capital Group, which lost $440 million in less than an hour. So we can classify the trading infrastructure as a mission critical system too, because of the potentially huge impact of the errors on the business world. The system under discussion is mission critical in that sense. It is a high capability trading engine developed by a company named Rodin Bourse, which is a spin-off of University of Tehran. It's going to be used by Tehran Stock Exchange, which is the largest stock exchange in Iran. So what's a trading engine? It's a central component of the back end of a trading platform. It receives order to buy or sell stocks from traders and brokers, and then it matches the incoming orders with the existing ones based on various criteria such as price or other criteria. And when two orders match, a trade is made as a result, and the clients are notified, and the market data is updated, and the post-processing take place. Other than the basic functionality of executing orders, it has interfaces for market administration. It exchanges the clearing and settlement data with the CSD, and it publishes market data to a vast number of consumers regularly. To give you an idea about how the matching algorithm works, I'm showing a very simple case of matching here. The engine receives an incoming order requesting to buy 1,200 shares of a certain instrument at a price of 60 or lower. At this moment, the order book inside the trading engine contains the previous unmatched orders sorted based on the price and then the arrival time. The order is matched against the orders of the opposite types. Here, the buy order can be matched with the first two orders in the sell queue based on the price, because the incoming order says I want to buy at the price of 60 or lower, so it can be matched with the price of 55 and 60. And as a result, two trades are generated with the price of the orders in the sell queue. The sell orders are traded completely, but as the total traded quantity is 800, the buy order is not matched completely. So the remaining part will be inserted into the buy queue, waiting for a matching sell order to come in the future. This was a very simple example, and different order types, different order qualifiers, and different matching algorithms are implemented in a typical trading engine. Like any other industrial enterprise application, trading engines offer a variety of functionalities. But the important point here is that this type of software is highly under pressure of non-functional requirements too. The most important of them is performance, which is somehow the main point of competition between different vendors in the market, of trading platforms. The large number of orders, including those issued by algorithmic and high-frequency traders, demand for sub-millisecond response time, which is very hard to achieve, especially in a distributed environment because of the network latency. And of course, there are other important quality aspects like any other industrial software, which makes achieving the desired performance even harder. All these requirements force the development team to use sophisticated techniques at all levels, architecture, design, and implementation levels. To give you an idea about how complex such a system is, I've listed a few characteristics of the system under study, among which I want to emphasize on one point, which is sequential order matching, which is a result of the fairness constraint. The fairness constraint forces the system to process the incoming orders on a particular instrument in the order of arrival. So this rules out clustering as the widely used solution to gain performance in enterprise systems. So the low latency must be achieved by optimizing the computation on a single thread. This results in decisions like not using exception handling in the core domain logic to avoid its performance overhead. So the main point here is that all these mechanisms to achieve quality affect the correctness of the system. And these mechanisms are not applied in a modular way, so that we can test the pure domain logic separately and then add or plug in the performance improvement modules to be sure still everything works fine. That's because performance in nature tries to break the boundaries of the modules and optimize the inter-module communications. So there's a serious need for comprehensive end-to-end testing, which includes all the non-domain parts of the code as well as the domain logic. At the time of the submission of the paper, the system had been under development for about 2 years, and there were a lot of automated test codes written by the developers in the form of unit tests and behavior-driven development style, BDD style tests, written in Cucumber framework. About 40% of the source code was the test code, which took about 30% of the development effort as estimated by the development team. This includes the maintenance and the refactoring of the test code itself. But as I said, a rigorous end-to-end testing was needed. And it had to be automatic because the team couldn't afford more effort on developing and maintaining the test codes. So we needed automatically generated end-to-end tests. And because of the complexity of the architecture and the source code, we could not use structural test case generation tools. So methods that relied on feedback from the source code, either statically or dynamically, were out of question. And as our main concern was ensuring about the correctness, we needed specified test oracles too. So we decided to examine a specification-based approach to test case generation. In this approach, the functionality of the system or some part of it is specified in some specification language. The test case generation algorithm generates test inputs based on the specification. The good point about this approach is that the specification can serve as the test oracle too. We examined several formal languages as well as programming languages as the specification language. Finally, we chose the functional paradigm for the specification. Our first tries were in Haskell, and we were quite successful in modeling computations over rich data structures. Then we were able to specify the behavior in a concise way because of the use of well-known higher order functions such as map, fold, filter, and etc. An important point here is that since we used functional languages just for specification, not for implementation, we could almost completely forget about performance issues and focus on writing a concise and readable specification. The part of the syntax of Haskell we used was almost the same as the specification language of Coq. So for a while, we switched the specification language to Coq so that we could benefit from the proof assistant in verifying that our specification meets certain properties. But as we went further, the developers with a basic knowledge of functional programming could read and write specifications, but proving with code was completely different story. So now we are not continuing with Coq and switched back to Haskell. Modeling system state is relatively straightforward. Algebraic data types are particularly useful for this purpose. Both Haskell and Coq provide convenient syntactic constructs such as records to provide a readable specification of data structures. The trading engine is basically a collection of services, and its functionality is divided into different request types. We define the behavior of the system in response to a specific request type in terms of a handler function, which is a function mapping a request and a system state into a response and the system state after the computation. This example shows the outline of a request handler. To keep the specification readable, we split the handlers into smaller functions. For example, the matching algorithm for by orders is specified separately in a match by function. Of course, I'm not going into the details of the algorithm. Another pattern that helped us to specify the system in a modular way was the decorator pattern. A decorator is a higher order function that takes a handler and returns a decorated one. It's like wrapping a handler inside another function, which calls the original handler, but it does some pre or post computations. The result is still a handler that can be wrapped by another decorator as well. For example, the minimum quantity check is a decorator that performs order matching by calling the handler on the request and the state. This happens here. But accepts the matching results only if the total traded quantity is more than a specified limit. The nice thing here is that since in the functional paradigm everything is immutable, we don't have to do anything special to cancel the trades if the condition is not met. We just return a reject response along with the original state. On the other hand, in the implementation, due to performance considerations, the state is mutated, and in case of such rejections, the matching algorithm must be rolled back, and it can be very complicated depending on the matching algorithm. Finally, we compose the decorators using the ordinary function composition operator, which gives an elegant description of the behavior of a request handler. To talk a little bit about test case generation, we used search-based algorithms to generate test suites. Unlike the normal case of search-based techniques, where the algorithms are guided by the coverage over the system under test, we express the fitness functions in terms of the coverage of the specification. We currently use simple expression coverage criteria combined with the test suite size, actually the negated test suite size, to keep the test suites as small as possible. We examined two search algorithms, simulated annealing and genetic algorithm. The genetic algorithm produced slightly better results, but they were comparable in general. We generated 10 test suites for each algorithm, containing on average 15 and 19 test cases, and each test case contains 10 orders. As you can see, the test cases are relatively small, and this is a strength of our method because with the small test suites, we could cover the code almost the same as the developer's test, as we will see. Both methods were capable of finding two important bugs, and it was very appreciated by the development team since they were not caught by their tests. The second bug was particularly interesting because it was due to the interaction of two features which were unit tested separately. And you see it's related to the rollback of the trace, as I mentioned earlier. This is our state when submitting the paper, but we continue to find bugs as the testing went further. To get an idea about the coverage of our tests, we selected a few classes which were related to the parts of the functionality that we covered in the specification. We calculated the branch coverage of our tests and found them comparable to the coverage of the developer's tests. Note that the classes contain code related to the features not covered in the specification, but removing those codes was not feasible since it would break many things both in the code and the tests. But as we manually check the uncovered parts, we observe that the test coverage is as good as the developer's tests. The same thing could be observed by mutation analysis on those classes. So apart from finding real bugs, we believe that the effectiveness of our methods is comparable to the manually developed test cases.
An issue that may have come to your mind is that it's like we're doing two-version programming here, one in Haskell or Coq, and another one which is the actual implementation in Java. In some sense, it is true, as it is for all types of specification. But to give you an idea about how these two versions differ, I bring an example here, which shows a credit limit processing, which checks if the broker had enough credit to perform the trades. So like other types of decorators, it first calls the input handler, which performs the matching and creates the trades. And then it checks if the resulting trades conform to the credit limit check. This is another function which is called here. Then it updates the credit information and returns the new state. Otherwise, it rejects the request and keeps the state as the same as the input state. The size of a complete specification for this feature, including the auxiliary functions, is just 75 lines. On the other hand, in the implementation, the credit management must be performed in a centralized way so that the orders on different instruments has access to the same credit manager component. So this credit manager component is deployed on a separate physical node than the trading platform. As a result, the communication infrastructure comes in, and the transaction management is needed to ensure that the updates are done consistently. So just to process the credit limit, we have about 1,000 lines of code here in the implementation. And this does not include the code to parse and validate the input requests and generate the output messages and so on. So actually, as I said earlier, although in some sense we are doing two-version programming, but these two versions differ in both size and in the fact that the specification is free from any technology or performance optimizations and so. To conclude, our experience showed that choosing the right tools for the right problem makes specification-based testing possible in practice. By the right problem, I mean a mission-critical system that is so complex that we can't assure its correctness by just unit testing the business logic. This is where the specification overhead pays off. To compare the effort needed by the manually developed tests and our automatically generated ones, based on the development team's estimates, the team spent about 800 man-days to develop, debug, and maintain test codes. In our case, it took about 60 man-days to develop the specification and develop the required tooling to both generate and execute the tests. And the fact that we gained comparable coverage with much smaller test suites makes it possible to include our tests in the CI/CD pipelines, which is very valuable in practice. There are two main branches that we're currently working on. The first is to define an appropriate notion of a specification coverage in our case. The basic question here is, how can we make sure that if we have a good coverage over the functional specification, do we necessarily get a good coverage over the imperative implementation too? For example, should we treat higher order functions like map, fold, or filter, or
something like this, which are commonly used in functional specifications in a special way, like requiring to cover both empty and non-empty list parameters. The other area is related to the fact that we are lucky that we have access to experts in the domain who can help us to enrich the fitness functions using domain knowledge. The important point here is that not all bugs impact the organization equally. Some may cost much more than others. By getting help from domain experts, we can assign weights to different parts of the specification and guide the test generation to the areas that the failure there have more impact on the business. So this is the second branch that we are currently working on. Okay. Thank you for your patience. I would be happy to hear your comments and questions, and thank you again.